A continuous torus of delocalized pi electrons surrounds the benzene ring, creating a protective barrier that actively repels most chemical attackers. This electronic shield provides exactly 150 kilojoules per mole of resonance energy. This specific energy value dictates benzene's unique behavior, separating its chemistry from that of standard alkenes. Addition reactions force an sp2 carbon to become sp3, permanently breaking the conjugation and sacrificing 150 kilojoules of stability. Substitution, however, replaces a hydrogen atom while instantly reforming the resonance shield. Thermodynamics favors substitution because it preserves aromatic stability. In the lab, alkenes decolorize bromine water instantly, without help. Benzene remains inert until a Lewis acid catalyst is introduced to strengthen the electrophile, overcoming the stability of the delocalized system. Navigating aromatic synthesis requires managing this 150 kilojoule per mole energy barrier, learning exactly how to break and restore it with precision. Between the starting material and the final product exists a temporary non-aromatic state known as the uranium ion, or the sigma complex. At this specific moment, the electrophile has attached, but the hydrogen hasn't left. One carbon atom is forced into an sp3 state, causing the aromaticity to vanish momentarily. Chemist George A. Olah proved this theoretical intermediate existed. Running reactions in superacids at -80 degrees Celsius, he isolated the uranium ion as a stable salt, using NMR spectroscopy to verify its structure. For providing the physical proof of this reaction mechanism, Olah was awarded the 1994 Nobel Prize in Chemistry. While the behavior of the uranium ion is predictable in benzene, the logic shifts when a halogen atom is already attached to the ring. This introduces the halogen paradox. These atoms mathematically drain electron density from the ring, yet they somehow direct new attackers to specific, highly active carbon positions. Every substituent raises two distinct questions: reactivity, how fast is the reaction compared to benzene, and orientation, where will the new group attach? The Hammond postulate links these questions. The activation energy required to reach the transition state directly reflects the uranium ion's stability. A more stable intermediate lowers the energy peak, accelerating the reaction. A less stable intermediate raises the peak, slowing it down. Substituents influence stability via inductive effects through sigma bonds and resonance effects through the pi cloud. The pathway that produces the most stable resonance structures for the uranium ion will always be the fastest and most preferred route. Activating groups, such as a hydroxyl group, use a positive resonance effect to donate lone pair electrons into the ring, stabilizing the uranium ion. This stabilization is geometrically restricted to ortho and para attacks. These positions allow for a fourth resonance structure, where every atom in the intermediate achieves a full octet. Conversely, deactivating groups like nitro groups use strong inductive and resonance withdrawal to pull electrons away. Attacking the ortho or para positions places a positive charge directly adjacent to the positive nitro group, creating severe electrostatic repulsion. Deactivators force attackers toward the meta position. This isn't because the meta position is active, but because it is the only pathway that avoids the highest energy repulsions. Electron donors accelerate reactions and direct to ortho-para positions. Electron withdrawers slow the reaction and force meta direction as the least disadvantageous route. Halogens represent a chemical contradiction. Their high electronegativity makes them electron takers, but their lone pairs make them potential donors. To solve the paradox, we look at speed and direction separately. Regarding speed, the halogen's negative inductive effect is stronger than its resonance donation, pulling overall electron density out of the ring. This drain raises the activation energy, making halobenzenes react slower than pure benzene. Regarding direction, during an ortho or para attack, the halogen's lone pairs can drop into the ring to neutralize the positive charge. This resonance rescue stabilizes these specific intermediates. The balance between electronegativity and atomic size creates a V-shaped reactivity curve across the halogen series, from fluorine to iodine. Halogens deactivate because their inductive pole dominates the overall speed, but they direct ortho-para because their resonance stabilization only functions at those specific nodes. The three categories of substituents represent predictable outcomes of competing electronic effects. Induction decides the speed. Resonance decides the direction. If resonance is stronger than induction, the ring activates. If both effects withdraw, it deactivates and directs meta. The halogen unique case occurs because induction controls the speed, while resonance controls the geometry. This prepares you for nucleophilic aromatic substitution, where these rules flip. In high-pressure reactions, fluorine becomes the most reactive leaving group. Mastering these structural principles allows you to deduce the behavior of any aromatic system from first principles. Practice this logic with our materials at the AROMA TRB Coaching Center.